Now let us study the applications of the universal gate and also find out the output for the universal gate, how we can get the required output, the desired output what we want, and what are the boolean expressions this desired gates or the universal gate perform. So first of all, let's study this circuit. The output, it gives x into x bar. That is, a NOT gate can be implemented using an AND gate. That is, here the output is x bar. Since the input is x and the output is x bar, x into x bar, that is x bar. Now, for simplification, I'll just show you the basic multiplications, how those are performed. Let's say multiplication, x into x is equal to x into x bar is equal to 0, x into 1 is equal to 1, sorry, x into 1 is equal to x, and x plus 1 is equal to 1. These are the simple formulas. Similarly, x plus x gives x plus 0 gives 0, x plus 1, x plus 0 gives x plus 1 gives 1, and x plus x bar, it gives 1. These are the basic digital binary boolean operations. What we have to remember, these are something which we need to remember, and these are of course very important while performing the boolean expressions. So let's say why these gates are called as a universal gate. So from this circuit we can check out a NOT gate can be implemented using an AND gate. That is, for this circuit, if we have this input, if we say this is the gate, okay, x, the output here will be x bar, x into x bar. That is, as I have shown previously, x into x gives x, therefore x into x bar also gives x bar. That is, if we give the output here as x, input as x, the output here is x bar. That is, the NAND gate here is performing the operation of NOT gate. Similarly, let us check with the other circuit. Let us say x and y. Okay, the output here will be x y bar. The output here also will be x y bar, and the total output here will be x y bar into x y bar, the whole bar. So as per the De Morgan's law, we can execute this as xy bar bar plus xy bar bar, which is again xy. Therefore, the NAND gate can also be implemented using an AND gate. As we can see, xy bar plus xy bar gives xy. That is, for precise understanding, I'll take this step here. Xy bar double bar plus xy double bar, which gives xy double bar is xy plus xy double bar is xy. So we can check out from this thing, xy plus xy, that is x plus x gives x, therefore here xy plus xy will also give as xy, which is again a AND gate. Okay, therefore a universal NAND gate can also be implemented as an AND gate. Similarly, a universal NAND gate can also be implemented as a NOR gate. So I'll just show the working for this also. Let's check how this is a OR gate. This bubble shows that it is a OR gate. Let this be x, this be y, this be x, this be y. The output here will be xy bar, the output here will be xy bar, and the total output will be xy bar into xy bar, the whole bar. By De Morgan's law, this breaks, that is xy double bar, this will be xy double bar, and this multiplication is replaced by addition, that is xy plus xy. Now let us take again the another example which can make us a clear idea about how this can be used as an OR gate. Okay, this is x x. So the output here will be x bar x bar. The output, total output for this circuit will be x bar into x bar the whole bar, that is x double bar plus x double bar, which will be x plus x is equal to x. This is a OR operation. That is, the NAND gate here can be used as a OR gate. Hence we have seen here that the entire operations what can be performed by the basic gates like NAND, AND, OR and NOT. All the three operations can be performed by the single NAND gate. That is the reason why the NAND gate is called as a universal gate. Similarly, the NAND gate the OR gate can also be used to perform the universal operations like what has been performed by the NAND gate. That is the reason why OR gate is also called as a universal gate. So the basic applications of the gates can be studied ahead later. The most important applications of the gate are, we can see, adders, subtractors, multipliers, and all these things what we have studied. So let us take one more example of an XOR gate, which is again not in the material. I'll just show you a brief idea what actually XOR gate is, how it looks like, and what are the truth table of the XOR gate. Okay. XOR gate, the symbol is like this. That is, these are the two inputs, X and Y. Okay. So I'll just show you the truth table for XOR. The output here is Y and it is denoted by X XOR Y. Okay. Let X be one input, let X be one input, Y be the other input, and the output can be, let us take it 0 0 0 1 1 0 1 1. These are the two different combinations of the input which we can put in the XOR gate. One input is X and the other input is Y. So the truth table for the XOR gate is 0 XOR 0, that is 0 XOR 0 is 0, 0 XOR 1 is 1, 1 XOR 0 is 1, 1 XOR 1 is 0. Just remember this table. Now I'll be showing it how we have got this output. Okay. Let us take the output as A. The basic equation for the XOR gate is A is equal to X bar Y plus X Y bar. Okay. So if we take this input, let X be 0, let X be 0 and Y be 0. So substituting these values in this equation, in the equation number A, we write it X is 0, therefore X bar will be 1, Y is 0, plus X is 0 and Y bar will be 1. That is, adding these two will give 1 plus 1, 0. Sorry, the output for this will be 0 plus the output for this will be 0. This will be 0. Similarly, let us take these two inputs. Let X be 0, Y be 1. The equation for XOR is X bar Y plus X Y bar. Now substitute this value in this equation. X bar will be 1, Y is 1, plus X be 0 and Y is 0. Therefore the output is 1. That is, when X is 0 and Y is 1, we get the output as 1. We can check out this. Similarly, if we take this, we get the output as 1. If we take these two inputs, the output is 0. So from the truth table of XOR, we can clearly see that if both the inputs are same, that is X is 0, Y is 0, or X is 1, Y is 1, the output is low. If any one of the input is different, that is, if X and Y, both the inputs are different, then we get the output as 1. Therefore, XOR gate are also called as inequality detector. That is, when both the inputs are unequal, we get the output as 1. When both the inputs are same, that is, when both the inputs are equal, we get the output as 0. That is the reason it is also called as a inequality detector. Now, one more important feature, one more important feature of XOR gate. I'll work out again and explain you in detail. Let's check out from the truth table X, Y, 0, 0, 0, 1, 0, 1, 1, and the output is 0, 0. It gives 0, 1, 1, 0. So this is the XOR gate. Okay. Let's take this example. If one input is 0 and the other input is 1, that is, let us consider one input is. So if any one of the input is 1, the output will be the buffer. That is, the output will be the complement of the other input, which is like clear from the input or the truth table. Here x is 0 and y is 1. Since one input is 1, that is y equal to 1 from this part, it is clear we have got the output as 1. Therefore, we can conclude that XOR X as an inverter when any one of the input is 1. That is, XOR X as an inverter to the other input when any one of the input is 1. Similarly, if we take 0, 0, that is, if any one of the input is 0, the output will be the buffer. The output will be the same. That is, XOR X as a buffer. That is, one input is 0, the output will also be 0. You can check out the same output as passed here. That is, here the XOR X as a buffer. Similarly, let us study the truth table and the working of XNOR gate. The only difference here is the bubble diagram. Let's take two input X and Y. The output equation for XNOR is X bar Y bar plus XY. Okay, and the truth table for XNOR is, let us say X, Y are the two inputs, 0, 0, 0, 1, 1, 0, 1, 1. The output will be 1, 0, 0, 1. If we put any of the values in this equation, we obtain the same what we have got here. Let us work out with this value. Okay, the equation is X bar Y bar plus XY, which is the equation for XNOR gate. So let's take this case where X is 0 and Y is 1. Therefore 0, X bar will be 1, Y bar will be 0 as Y here is 1. Similarly, X is 0 and Y is 1. Therefore the output here will be 0. You can check out. That is, we can clearly conclude here from this that XNOR X as a buffer when one of the input is 0. XNOR X as an inverter when one of the input is 0. That is, it gives the output which is the inverted or which is the complement of the other input. You can check out. Similarly, if one of the input is 0, XNOR X as a buffer. That is, for example, if both the inputs, let us say for example 0, 0. Okay, for this case, since one of the input is 0, the output here again will be 1. That is, XNOR here is acting as an inverter to this gate or to this output. Hence we conclude the basic working of the gates and the operations what the basic gates, the universal gates perform.